the previous lecture, we've introduced the syntax of propositional logic. In this lecture, we shall discuss its semantics. Let's first consider an example. You may think of an abstract proposition, such as A and not B implies B, as a little program for a device with two input ports, labeled A and B, and a single output port. The idea is that this device transforms truth values offered at its input ports into a truth value offered at its output port. It's convenient when specifying the input-output behavior of such a device to concisely denote false by a 0 and true by a 1. Then this device will, when we offer it two zeros at its input ports, produce a 1. And when we offer it a 1 at the input port labeled A and a 0 at the input port labeled B, then it will produce a 0. Now the purpose of a semantics is to associate with every abstract proposition an input-output behavior. And we shall explain in this lecture how this works. And we will start with explaining the input-output behavior of the individual connectives. Let's start with fixing the input-output behavior of negation. Intuitively, the negation of an abstract proposition P should be true if P is false, and false if P is true. A clear and concise way of communicating this meaning of negation is to present it in a so-called truth table. In the first column, under P, we list the two possible truth values that P may have. In the second column, under not P, we list the truth values not P will have given the truth value for P at the same row. If P is 0, then not P is 1. And if P is 1, then not P is 0. Let's now consider conjunction. Intuitively, the conjunction P and Q should return true only if P and Q are both true, and it should return false otherwise. To record this information in a truth table, we should list all possible combinations of truth values for P and Q in the first two columns, and then put, for each combination, the appropriate truth value of P and Q in the third. If P and Q are both true, a situation that corresponds with the last row of the table, then the conjunction P and Q should be true as well. In all other situations, the conjunction should be false. We proceed to discuss the meaning of disjunction. Intuitively, the disjunction P or Q should return true if P returns true or Q returns true, and false otherwise. Let's try to fill a truth table for disjunction on the basis of this intuitive description. From the intuitive description, it's clear that if both P and Q are false, then P or Q should be false too. Furthermore, if one of P and Q is true and the other is not, then the disjunction should be true. The question that remains is, what should be the truth value of P or Q if both P and Q are true? You may want to pause the video for a moment and think about this yourself. We should make up our minds on whether we want to put a 0 or a 1 in place of the question mark. Before we do so, let's note that both interpretations of OR appear in everyday language. On the one hand, consider yourself in the situation that you're stopped on the street by a policeman and he asks you for identification. He might ask, "Can you show me your passport or driver's license?" Now, clearly, the policeman will not arrest you if you show both. So this is an example of the so-called inclusive interpretation of OR. On the other hand, a question that I might ask my daughters in the morning when I make them their sandwiches is, "Do you want peanut butter or jam on your sandwich?" Now, when I ask this question, I mean that they make a choice. I'm not willing to put both on their sandwiches. So this is an example of the so-called exclusive interpretation of OR. In logic, in mathematics, or actually in science, we cannot tolerate ambiguity, and therefore we cannot leave open whether disjunction refers to the inclusive or exclusive variant of OR. The choice is fairly arbitrary, but it has to be made. Disjunction in propositional logic refers to the inclusive variant of OR. We now come to defining the interpretation of implication. The implication P implies Q is true if the conditional statement if P then Q is true and false otherwise. The truth table for implication turns out to be counterintuitive for many at first. So before we give it, let us first give you some intuitive appreciation of the interpretation of conditional statements. Suppose that I make the statement, if it is sunny, then I'll treat you to ice cream. And let's now consider 4 situations and evaluate whether I've made a true or a false statement. First, suppose that the weather is sunny and I give you ice cream. Then I think you'll agree with me that I've made a true statement. Next, suppose that I give you ice cream in very bad weather conditions. Then still, I've made a true statement. I said that you would get ice cream when it was sunny. I didn't say that you wouldn't get ice cream when it wasn't sunny. Next, consider the situation that we have the same weather conditions, so it's raining cats and dogs, and I don't treat you to ice cream. Then you may be disappointed that you don't get ice cream, but I've not made a false promise. Finally, consider the situation that you do not get ice cream, but actually the weather conditions are that it is sunny. Only in that situation, you may accuse me of a false promise. I promised you ice cream when it was sunny, and now apparently I don't give you ice cream. Let's now present the truth table for implication. The only situation in which a conditional statement P implies Q should be considered false is when the condition P is true, whereas the conclusion Q is false. In all other cases, the conditional statement is true. The last propositional connective we should consider is by implication. P by implication Q is true if P and Q have the same truth value. The truth table for by implication is straightforward. If P and Q have the same truth value, both false or both true, then P by implication Q returns true. If P and Q have different truth values, one of them true and the other false, then P by implication Q returns false. Let's return to the example with which we have started this lecture, and let's associate an input-output behavior with the abstract proposition A and not B implies B. To compute a truth table for this abstract proposition, it's important to know in which order we should compute the truth values for the constituents. Note that we have omitted a couple of parentheses from this abstract proposition. It's convenient to reintroduce them so that we know the order of computation. To compute a truth table for this abstract proposition, we should first compute truth values for not B. Then we should compute truth values for A and not B. And finally, we can compute truth values for the entire abstract proposition. In other words, we always work inside out. According to the truth table for negation, to find appropriate truth values for not B, we should invert the truth values for B. To find appropriate truth values for A and not B, we should consider the truth table for conjunction. If A is equal to 0 and not B is equal to 1, then the conjunction returns 0. If A is equal to 0 and not B is equal to 0, then the conjunction returns 0. If A is equal to 1 and not B is equal to 1, then the conjunction returns 1. And if A is equal to 1 and not B is equal to 0, then the conjunction returns 0. Finally, to find appropriate truth values for A and not B implies B, we should consider the truth table for implication. According to the table, an implication is false only when its left-hand side, in this case A and not B, is true, and its right-hand side, in this case B, is not. This is only so in the third row of the table. On all other rows, we should therefore put a 1. We have computed the truth table for the abstract proposition A and not B implies B using the truth tables for the connectives. This table unambiguously describes the input-output behavior of the device with which we started our lecture. The device apparently produces a 0 only if we put a 1 on the input port labeled A and a 0 on the input port labeled B. In a similar way as we have done for the abstract proposition A and not B implies B, you can now associate using truth table semantics an input-output behavior with every abstract proposition. This concludes our presentation of the semantics of propositional logic.